So let's take a look at the next example problem from the exam, 5.23. Here we have a beam which has a horizontal component and a tilted component. It's subjected to a distributed load. That distributed load, in terms of the roller at A, will tend to introduce a clockwise rotation. The reaction at B has to oppose that. You can make the same argument for how the reaction at A has to oppose rotation about B. The reason I say that is you can see that both of these values are going to be directly related to the basically magnitude of this force density or distribution of force. So when I copied this over, I put a capital W, but what they're really looking for is the height of this density function. So naturally, you see that as its value increases, the necessary reactions at A and B will increase as well. So what this problem is looking for is if you were limited in terms of the reactions that could be sustained at A and B, how much of a load could you bear? So it's a little bit of a non-traditional problem in the sense that it's not just given a load, find the reactions. It's given restrictions on the reactions, find limitations on the corresponding load. So probably not the best exam problem because it's a little bit not straightforward, although it's not overly complicated. So the first thing, when in doubt, draw a free body diagram, at least in this class. It may not work in the rest of the world. I wish I could draw a free body diagram and make it cooler in this room right now, but I guess we'll have to save that to thermodynamics, and we don't teach that here. So bad engineering joke, sorry. It's late. So hopefully I did a decent job of representing that. Now, what would all of the individual forces look like? Well, since we have a roller at A, it can't oppose translation along the surface. It can only exert a single normal force, and that's going to have a geometry that we'll talk about in a minute, but that is the reaction at A. We know this is a 30-degree angle, even though it's drawn much bigger than 30 degrees. We know that the length of the kind of tilted portion of the beam is 3 meters. We know that the pin in B, we can represent the reaction forces by an unknown vertical and horizontal component. And we know that if we assume the wrong signs, then we will just work that out after the fact. And we know since this load distribution is uniform, I can replace it by a single equivalent load, which is going to be located right in the center of the distribution, meaning that if I draw kind of a reference line, this will be 2 meters. The separation from the single equivalent load to point B, in the same fashion, that will be 2 meters from the kind of center line of that load to the bend in the beam. This distance, if you know that that distance is 3 meters and you know that this is 30 degrees, will be 3 cos 30. And in a similar fashion, the height here, which will be important in a minute, will be 3 sine 30. Now, how can we relate the magnitude of this load to the kind of intensity or height value of this distribution? Well, remember that the way you generally get it is to take the width, you get the area under this curve. And since it's a rectangle, the area under the curve is just the width times the height. So this is just going to be 4W in terms of the lowercase w, or the intensity value. You can work this a couple different ways. You can find the equivalent load and then map it back by dividing by 4, or you can just work this with 4W the whole time. They both work the same way. The only thing we need to do, just in case it's not obvious to anyone, if I had a standard kind of XY coordinate system, if I lift the horizontal side by 30 degrees, which is what they did when they created this bend in the beam, that will effectively shift the vertical by 30 degrees as well. So this is the normal axis. This is the direction along which that force is of the roller, the reaction. So if this axis shifted by 30 degrees, this shifted by 30 degrees as well. The reason I'm showing you this is if you notice, if I were to decompose this into a traditional Y component and a traditional X component, the X component is actually, let me zoom in a little bit. Sorry, that's so squish. The X component is opposite the 30-degree angle, and the Y component is adjacent. So I can say that A basically can be decomposed into whatever that magnitude is of that normal reaction. The Y component would be cos 30, and the X component would be sine of 30. So a lot of times you'll see like they draw this angle as well. They'll say, oh, that's 30 degrees. And same logic, right? The X component is opposite. The Y component is adjacent. So however you get I think a lot of you have probably seen that kind of geometry trick in a physics class before, so probably don't need to spend any more time on it, but just wanted to show you that just in case. So if you think about it, ultimately what you want to do here is relate um, the magnitudes of the reactions to this small w value, which is the intensity of the distribution. And when in doubt, the way that you generally go about these problems, and you'll kind of see why I did this after we shake it out a little bit, is to compute a moment about one of the reactions, particularly the one that would basically allow you to eliminate an unknown. So if you think about applying or enforcing equilibrium about point B, saying that the sum of all moments about point B has to be zero, you'll be able to directly relate A to W. So then moving forward, any equation that involves A, you'll be able to write it in terms of W. And if you can do that, then you'll be able to relate W to B, and you'll be able to go on from there. So let's see how that would go about. So let's enforce rotational equilibrium about point B by saying that the sum of all moments about point B has to be zero. Let's determine what that would be using scalar type analysis. Notice if we pin at B, the load will induce a counterclockwise rotation, so that will be positive. So I'll say positive 4W times, what is that perpendicular distance? Well, if you notice, the line of action is vertical, so the perpendicular distance is just 2 meters. I'm going to just assume that all the units are going to work out, and this will be in kilonewton meters, because the values that I'm given here for forces are all in kilonewtons per meter, and my distances are all in meters. So that's the rotation of the load about point B. Now I could manually try to write an expression directly for A and find what these perpendicular distances would be, but that's going to be very confusing. If you think about just decomposing A into a y and an x component, then the perpendicular distance for the y component is just the total horizontal displacement from B. So I'm going to take the y component of A. So first let's determine what the sign would be. If you pin at A, if we assume the normal acts in the traditional direction, the y component would induce clockwise rotation, so it's going to be negative. The y component of A is A cos 30, and it's going to be at a perpendicular distance of 2 plus 2 plus this. So I'll just write 4 plus 3 cos 30. Now, what about the x component of A? The x component of A will also induce clockwise rotation, so it's going to be minus. The x component has a magnitude of A sine 30. And I hope this isn't confusing anyone. Like when we did the last problem, it's like, oh, the x component doesn't contribute rotation. Well, remember, in this case, the x component actually has a perpendicular distance. It's separated from point B, and that distance of separation is basically the vertical displacement associated with this, the tilted portion of this arm. So that's this perpendicular distance is the 3 sine 30. So hopefully that makes sense to everyone. And that all has to be equal to 0 if this thing is in equilibrium. So what I can do is actually write an expression for W in terms, or for A in terms of W. You could do it the other way around too, but what we'll ultimately be interested in doing is to simplify our analysis moving forward to substitute in for anything that involves A an expression for W. So let's do that. So let's move both of these terms to the other side, and we'll write A times, from this term, we'll have cos 30 times 4 plus 3 cos 30. That's from this term. From this term, we'll have plus sine 30 times 3 sine 30. And that whole thing is going to be equal to 8W. So A is going to be nothing more than 8W divided by, so the 8W came from 4W times 2, divided by this ugly thing in the denominator, cos 30 times 4 plus 3 cos 30. So it looks ugly, but it's just basically, that's just a distance, right? That was that perpendicular distance. This cos 30 was what we needed to do to decompose into x and y components. And then over here, we just got 3 sine 30 times sine 30. You can write it as sine 30 squared, but I like to keep them separate just to make sure that we can have a clear picture of what's going on. So what I need to do is basically I'm going to take and get a coefficient for W. So I'm going to take everything that doesn't involve W. So cos D 30 times 4 plus 3 times cos D 30 plus 3 times sine D 30 times B30 close. And what I get is that A is equal to 1.2376 times W. So, and that makes sense if you think about what we talked about at the beginning. Basically, as the density of the distributed loading increases, the reaction at A is going to have to go up in order to counterbalance the rotation about B. That's all that's saying. As the density of that distribution goes up, the value of A has to go up as well. So there's multiple ways to approach it for now. I'm going to make sure I have an additional piece of paper. Sorry about that. But the easiest thing to do is probably just to now enforce translational equilibrium. So usually your sum of all x and sum of all y equations are easy because you don't have to think about those horizontal lever arms. So let's just, for example, sum all forces in the x direction with the standard positive to the right type convention. So what forces do we actually have to the right here? Well, if you think about it, it's just the x component of the reaction at A and the x component of the reaction at B. So what that means is that the x component of the reaction at A, which is A sine 30, and by the way we've drawn these, it would be plus bx. Those have to be equal to 0. But we could rewrite A, sorry, that's ugly, looks like sine. We could rewrite A in terms of W. So this is just going to be 1.2376 W sine 30 plus bx equals 0, which means that bx is just basically going to be minus 1.2376 W times sine of 30, right? So that minus is just showing us that the direction we assume for bx is wrong. Now let's sum all forces in the y direction and set that equal to 0 with the standard up convention being positive. So that would be the y component of A, which is going to be A cos 30. Don't forget you have your minus 4W going down. I'm kind of going back and forth between making this a capital W and a lowercase w, but we haven't really did the centroid section yet. The book weirdly introduces these distributive forces beforehand. So, we can be a little bit messy with our notation. And don't forget the y component of the reaction at B. And remember, you can substitute in for A, 1.2376 W cos 30 minus 4W plus BY equals 0, which means that BY is going to be equal to 4W plus 1.2376 W cos 30 degrees. So let's actually compute what these two things turn out to be. And I will just say BX equals BY equals, and we're going to go to a calculator here. So for the x, I need to take minus 1.2376 times sine b of 30. So that's going to be minus 0.6188 W, minus just meaning we assumed the wrong sign. And for, let me actually go back to the .cam and show you. I assume it's obvious given how complicated the problems you all have worked in the course so far. But I can factor out the W here and just write this as. So when you see me put this term into the calculator, that's why I'm doing that. So that would be 4 plus 1.2376 times cos d of 30. I can get an expression for y is 5.0718 W. Okay, so let's think for a minute what we know. So we want what? We want mag B to be less than 7.7 kilonewtons, and mag A to be less than or equal to, up to, probably just less than. It's a little bit ambiguous, but we'll just say less than for now. You'll see it won't really matter in terms of our answer. But we know that the roller at A can support a load of up to 3.3 kilonewtons. So these are all, if you think about it, restrictions. These are restrictions for B, and we already have our restriction for A. A is equal to 1.2376 W. And what these are saying, just to go over it again, is as W goes up, A has to go up, right? So it would help if I went to the .cam. That way you can see what I was writing. As W goes up, A has to go up. As W goes up, the X and Y components of B have to go up. So in order for A to be less than 3.3 kilonewtons, another way to write that is for the A restriction, 1.2376 W, that's A, has to be less than 3.3 kilonewtons. In order for that to be true, W must be less than 3.3 kilonewtons divided by 1.2376, which is going to be equal to, so we'll just write the less than again, 3.3 divided by 1.2376, 2.67 rounded to 36 kilonewtons. So thus we'll say W must be less than 2.67 kilonewtons to meet the A constraint. And what we're going to find, I mean, these aren't going to be independent constraints. What will likely happen, and as is often the case in engineering design, one of these constraints will actually turn out to matter in this particular case. So let's do the B constraints. But if you notice, since the constraint on B is on the magnitude, we'd want to say, take our expressions for bx and by, and we'll say mag b is just the square root of bx squared plus by squared. So you could write that as square root of minus 0.6188 w squared. Let me show you just how this math works, just in case you're a little bit confused. Plus 5.0718 squared w squared. So remember, when you square a product, you can square each term individually. So that's why this is this should be squared here. Sorry, I said it and I didn't write it. So you could factor this out. What happens is you factor the w squared out underneath the square root, and I'm just going to ignore that this is negative for the time being, since when I square it, I'm going to get a positive anyways. Okay, and remember, when you have a product under the square root, if you have a perfect square, you can pull it out. So you can say it's equal to w times square root of 0.6188 squared plus 5.0718 squared. So let's actually put that in the calculator just to make it a little bit simpler here. So square root of 0.6188 squared plus 5.0718 squared, and that is going to be 5.1094. So that is this restriction on B that we actually have, which we're just calling mag B. So in order for that to be less than 7.7 kilonewtons, what that implies is that W must be less than 7.7 kilonewtons divided by 5.1094, which is going to be almost there. Sorry, this is a long one. It's one of these things, I'm sure if you worked in and got it right yourself, you're like, man, I wish it would go quicker. But if you didn't know how to set the problem up, I wanted to make sure I showed you enough to make it meaningful. So the restriction on B is going to mean that W has to be less than 1.51 kilonewtons. So if you think about it from a dominating point of view, the restriction on A says you have to be less than, just call it 2.6. Yeah. Anyways, this number is larger than this number. So what is really limiting you in your mechanical design is the limits of the magnitude of the reactions of B. A says just keep it below 2.67 kilonewtons. B says keep it below 1.51 kilonewtons. So we say thus W must be less than 1.51 kilonewtons. It turns out that the constraints at A don't matter. We're not actually pushing those because of the way that this geometry is laid out. And hopefully that's not overly surprising to you, because what's happening, the reason that this is, if you think about overcoming rotation about A, this distributed load is quite a bit away from it. There's this big lever arm causing this rotation. So there's really a lot of rotational stress on B to counterbalance. That's not rotational stress per se, but the magnitudes of these reactions must be large to counterbalance the rotation of the distributed load about A. So versus when you compute it about B, A's got this big lever arm versus the distributed load is pretty close to B. So hopefully that gave you some physical intuition and helped this problem make a little bit of sense. like I said, it's probably, if I had to, of all the ones we've done so far, if I had to call one, maybe a little bit not challenging for the exam, but again, the last thing you want to do on an exam is take someone that's really prepared and throw them off with a problem that's just a little bit tricky. So I do generally like my exam questions straightforward. I don't consider that easy. I just consider like you give these types of what if and design problems on homework and in the exam, just make sure that everyone has what they need to go on.